We're going to think about geographic concepts today. Right? You can't make effective maps unless you understand the basic concepts that go into making maps. And the first thing I want to cover is mental maps. These are maps of the environment stored in our brain. They reflect our geographical knowledge and the spatial awareness that we possess. And there are varying aptitudes of spatial awareness among everyone in this room, of course. And a lot of it will depend on how much experience you have in a given location. So the first thing I want you to do is pull out something to write with. If you don't have anything to write with, you can do it on your computer, pull up Paint or something. And I want you to draw a mental map of Bozeman. We're going to take about 4 minutes to do this. If you're just coming in, just grab a piece of paper. We are drawing a mental map of Bozeman. Things that are important to you, landmarks, maybe routes that you take normally, whatever kind of comes to mind. Give you about 1 more minute to finish this up. If you're making a masterpiece, you can work on it some more later. All right, so this is what I came up with up here with my Sharpie and not great art skills. But what I want you to do is talk to the person next to you, compare and contrast your maps, and think about what is different between your maps. Like why did you choose to map certain things in comparison to the person next to you? What are some of the major differences? I want to jot some of those down in about 3 minutes. Ready to go. All right, everyone's quieting down on your own. So I'd love to hear some sort of observations about what was different between your map, person next to you, your map, my map, whatever. And if you wouldn't mind, if you raise your hand, if you could just say your name and what you're studying, I would love to hear that as well. Yes.
The guy had migration up.
Cool. So Brian kind of centered the map. Where did you say you centered yours? Off Main Street. Yeah, and I kind of started, the first thing I drew was my house. And I really focused in on transportation. So it probably depends on where you live, where you're most familiar with. Raise your hand if you centered your map on campus? Quite a few people. Main Street? Top of Slushman's Lift at Bridger Bowl? Anyone? No. Not snowing yet. Cool. So the origin of the map, let me make some notes here. We'll call it the origin or the focus was different. That's really going to depend on what you want to show on your map. How could we actually describe the origin of our map? Yeah, so like if we were using a computer to make a map, we could describe the very center of the map with like an XY coordinate. Yep. And what's your name and what are you studying? Cool. How you look at what? How you look at what? Yeah. Yeah, that's great. So orientation, that's a big one. This is one that, you know, by convention, most people growing up in our culture, looking at the maps we typically see, we're going to have north being up, but maybe you oriented your map differently. Raise your hand if you oriented your map some other way than north being up. And it's totally okay. You're not kicked out of the class or anything. Awesome, like maybe 10 people max. So that just shows you how common map conventions are, right? When we're designing maps, we want to think about what our audience actually is looking for. And if we have a map that is oriented with that kind of breaks convention, we really want to make sure that that's clear. So you'd want to provide a north arrow. You know, I did provide one on my map. A lot of times it's okay to drop the north arrow if you are conforming to those conventions, right? People, if you don't see a north arrow, it's a safe assumption that north is up on the page. Other differences. Yes. Awesome. Yeah. So Tom is noting here that map scale was really different. Like you know, my map scale is probably a rough approximation, but I included everything from the airport out in Belgrade all the way down to the Gallatin Range on my map. So we're going to talk a lot about scale in this class. And how do we actually define scale? So scale is sort of the conversion factor that goes from the real distances on Earth to what you're representing on the page. So, for example, you know, it's about 2 miles as the crow flies, my commute from my house to work. So this distance here on my map might be 2 miles. Let's call that an inch. We can provide a map scale here. 1 inch on the map is equal to 2 miles. If we wanted to get a fractional scale, which is what you'll commonly see reported on professional maps, you could say, you could convert that 2 miles into inches, get rid of the units on the top and the bottom of that fraction, right? We can also think of this as 1 inch over 2 miles. That's the number you'd have to multiply the distances by to convert them to the map distances. And that would be a type of scale we use. What we could also do is provide a scale bar, right? I could draw like a graphic here, have 2 miles, something like that. So whose map was a more detailed scale or showed a smaller area than my map? Raise your hand. Cool, maybe showed a broader area, anyone? All right, maybe somewhere similar to mine could be a third option. Any other differences? Yes. Naming of places, what you chose to actually label on your map, and what's your name and what are you studying? Awesome. Yeah, I work with a lot of paleo students. Cool, so what you actually chose to label on your map, what's one thing you labeled that I did not? Nice, so landmarks that are important to you. So I do a lot of like road bike riding and I do a lot of driving around town. So for me, you know, I labeled a lot of the roads on here that I travel. You know, for instance, if I want to go to Gallatin Canyon, go up to Big Sky, I can choose. I can either go over Gooch Hill or I can go down South 19th and loop around. Or I can take West Huffine out here to Four Corners, etc. Maybe that was on my mind because last weekend I went up to Big Sky to do a mountain bike race, which was a lot of fun. But yeah, if you're primarily a pedestrian and primarily walking around campus, maybe you labeled buildings on campus. Maybe you had more familiarity with fields and sidewalks, etc. So let's call it the thematic or reference layers on the map. And also like choice of labels. I'm also going to hazard a guess that some people's artistic abilities are a little bit better than mine. I'm better at using software to make nice looking things than I am at drawing them by hand. Or maybe it was actually worse than mine, but we're going to have a range of artistic abilities, right? And sort of design senses. And one of my goals in this class is to teach you better design strategies that you can use in GIS to make really effective maps. For example, I might have, if I wanted to highlight some things on this map, I might have chosen a different color, different line weight, etc. I just showed up with a random Sharpie I had in my bag, so didn't have too many things to work with. Other differences. Anyone use a different symbol for a road? Like maybe you dashed a line, different color, stuff like that, right? Symbology differences. So this exercise really meant to get you thinking about all the different things that you can vary on a map to change how the map is perceived, to change what information is conveyed, all of those different things. So thanks for playing along. All right, so from your textbook, there's a few examples. The author of your textbook is a professor at UCLA, so a lot of the examples are from Southern California, but just some different, mental maps, right? This is a very general one showing like a coastline, an ocean, a polygon demarcating where Santa Monica is. Right, here's one that looks a little bit more like mine, except it used a mountain symbol instead of just drawing letters or just words on the map. Right, a couple of different symbols showing settlements, airports, mountain ranges, roads. And here's an even more detailed version, a little bit more accurate, showing more roads, important landmarks, etc. All right, any questions or comments before I move on? Cool. So we're going to talk about some geographic concepts for the rest of today's lecture. And it's really important to remember that GIS relates questions about what, when, how, and why to where, right? These are fundamental principles of geography. What, when, where, how, why, right? And what a GIS enables is adding that spatial component to it to answer those questions. We talked last time about how a GIS combines spatial and attribute data. We can take like basically a table full of values, attributes, and tie them to locations on Earth. Those locations can be represented by points, polygons, lines, or surfaces. And they can be layered on top of each other. And this is a cool map I found, kind of an animated map, just showing us that September in Bozeman is actually when we start to see the peak fall foliage during the 3rd week of September, so not too far away. I have to confess, I was going through the Starbucks drive-thru yesterday with my daughter who was very hungry, and I tried to order a pumpkin spice latte, but they were totally out, which was a bummer, even though it's still August. So let's revisit these questions of the W's of geography, right? The what, when, where, why, and how. And I want to think about a hurricane. Is a hurricane currently affecting Florida? Idalia, I think, is the name. So having a spatial component to these questions allows us to fully understand what a hurricane is, why it might occur, where it might occur, when, and etc. So what is a hurricane, right? It's a little bit of Earth 101 content here. What fuels a hurricane? One of the important things about understanding a hurricane is that they are really fueled by warm surface temperatures of the oceans. What that creates is a lot of evaporation, a lot of water vapor gets into the air, starts circulating, and can eventually form into a hurricane. Another thing we need is a Coriolis force, something that only exists at certain latitudinal ranges. We don't have a strong Coriolis force at the equator. So that tells us that if we're mapping hurricanes, we're looking at specific areas of the Earth where they're likely to occur. This was a map I downloaded yesterday from a great site that has lots of really cool examples of GIS maps, googlemapsmania.blogspot.com. It's actually linked to in your chapter 1 reading. But This map is using a few different strategies to show what's going on with this hurricane, where it's expected to make landfall and cross over the state of Florida and Alabama, and then where it's predicted to go in the next few days. We can also infer some things here about how the symbology communicates what's going on. You can see some white arrows showing us wind patterns. We also have these zones that are colored, and these are actually referred to as isorhythmic zones. They're basically contoured areas on the map showing us wind speed intensities, and those correspond to our legend down here showing us what are the most dangerous areas in this hurricane. So this map can be used to answer the question of when, right? If I am in the track of this hurricane, when will it hit me, or when should I get out of there, evacuate to avoid the dangers of the storm? We can also use maps to answer the question of where, right? Where do hurricanes typically affect? There was also a tropical storm hurricane a few weeks ago that actually impacted Southern California, which is pretty rare. We don't hear about that a ton of times, but this map shows us historical hurricane tracks. And we do note from this map that they do actually occur in the East Pacific Ocean off the west coast of Mexico up into Baja California, but most commonly they affect the Gulf of Mexico and the Southern Atlantic Ocean. Anyone have any ideas about why these hurricane tracks are shaped the way they are? Yes. Yeah, I love the answer, Gulf Stream. There are a bunch of major currents in the ocean that are in part affected by predominant wind directions. So our Earth's circulation system really affects which direction a hurricane heads in based on its latitude. Notice that hurricanes do not exist down in the latitude range of just the bottom of this map, right? That's the equatorial region where we don't have that rotational force to set these hurricanes in motion. They tend to form in the tropics, which we might infer is a place where we get the most incoming solar radiation, right? The most energy from the sun, creating heat, giving these storms that energy to get going. They start by moving east to west. They move to the north and they curve off and head off to the east. So that is primarily controlled by ocean circulation patterns and the predominant wind directions we see at these different areas on the map. So down here to the south, we typically get east to west winds, easterlies. As you go to the north, we get westerlies, winds coming out of the west, blowing to the east. And as we just had an answer about, right, why do hurricanes happen where they do? We need to understand other natural phenomena that can be communicated on maps, one of which would be the ocean circulation map on the top of the screen here, showing us what we call gyres, which are important circulation patterns of the ocean. Down here in the bottom, we have a map with a surface showing us the sea surface temperature. So we typically get a lot of hurricanes in these regions where we have warm ocean temperatures. That's another reason why hurricanes stay on the track of moving up along the Gulf of Mexico and along the eastern seaboard, is because we have warm water in those locations. Hurricanes don't typically make it to Northern California because the ocean is too cold there to continue fueling those types of storms. So maps, geographic information, and particularly the question of where features occur really helps us probe and understand these natural phenomena. This is actually a map you will make in this course as part of your lab. Someone asked me last time what was one of my favorite maps to make. I think this is my most artistically inclined map. This is part of our lab we call cartographic design. And we will teach you how to make really attractive maps that look like this. Some of the interesting things about this map is we have a map projection focused on the South Pole. This is called a mnemonic projection. We're going to learn all about what those terms mean here in a couple weeks. North is not up on this map in all places, right? Actually, all directions on this map are north because the center, the focus on this map is the South Pole. So if you go to the right, that's north. You go to the south, or you go down on the map, that's north, etc. All right, so we've talked about the W's of geography, how we can use a GIS and maps in particular to answer these questions, better understand natural phenomenon with a location component. So I want to define that term for you, location. It's basically the position on the surface of the Earth. There's 3 types of locations. I'll go through those one by one. I want you to learn this term called geocoding. This is something you should know about in GIS because you will use it frequently. And we're also going to spend some time in this course talking about and working with GPS data. You'll actually have a lab where you go outside, use your smartphone or other device to collect GPS coordinates, global positioning system. All right, so how can we describe our location today, right? We're located in Bozeman. We're in Romney Hall. We're in room 8. Here's a satellite image of Romney Hall when we had some more construction going on, probably from a couple of years ago. And so all of these descriptors I've just used are referred to as nominal locations. We are describing our location based on landmarks, right? So it really depends on our knowledge of different landmarks. If you told someone from New York City, hey, I'm located in Romney Hall today, they've never been to Bozeman, it's meaningless, right? But to the right audience, this type of location information is very meaningful because they might know where Romney Hall is. We can also describe our location with respect to other locations. Like we are adjacent to Gaines Hall, just to the east of Gaines Hall. We could also use absolute locations to describe our position. And we have a whole bunch of different schemes for doing this in a GIS. Someone earlier mentioned XY coordinates to describe the center of the map. And yeah, that's a great option, right? So absolute locations require us to use a coordinate system. One of the next things we'll do in this course is look at different coordinate systems and how they are used. But a lot of the times you can think of this as an XY or Cartesian grid just draped across your map. We could think of our origin down here at 0, 0. Might be 20 meters east, 20 meters north. So we could describe the location of this point here as 20, 20. Or it could be a latitude, longitude. It really just depends on whatever coordinate system you are using. So you've probably all heard of latitude and longitude coordinates. What I'd like you to do now is if you have your phone or even your computer, you can go to Google Maps. I want you to try to find your GPS location. I'll show you how I would do that on my phone. So I'm one of these weird people that likes to make my family all have trouble sending text messages with an Android phone. I even saw recently, like, you are ruining your family's communication if you own this phone, but I like my phone. So I would fire up Maps and just wait for my location to pop up. One of the cool things that I can see on my screen here is actually a circle that shows us the estimated precision of the location. And so what's going on in this phone is it's using my IP address where I'm connected to the internet. It's also communicating directly with satellites. Isn't that kind of crazy? You have a computer in your pocket that is talking to satellites. It's getting signals from them and calculating your distance from orbiting satellites. And that can tell you your location. It's telling me my location accuracy is low. That's okay. But if I just kind of click and hold on the map, it'll bring up a nominal location at the top, right? Near Romney Gym, Bozeman, Montana. Gives me a zip code as well. Given my absolute location, 45.66 degrees north, 111 degrees west, or negative 111, meaning we are to the left of the prime meridian over in England. Below it, this is kind of interesting. This is a different coordinate system that's encoded a different way, right? But we can pull up our GPS location just using our smartphone, which talks to satellites. I want to also talk a little bit about precision of these measurements. So one thing you probably note is that if you are looking at your phone and it's telling you 45.6653692, right? That's 6 decimal places. We can refer to this comic by one of my favorite comics, XKCD, lots of good GIS content in there, to see what kind of precision this number is claiming. So this is literally precise enough to actually, well, we're somewhere between pointing to a specific person in a room and pointing to Waldo on a page in Where's Waldo, right? So really precise. However, when I actually look at Google Maps, it's giving me a huge radius that encompasses the entirety of the Romney building. So my point here is I want you to be a little bit careful when you're reporting locations. Think about your precision, right? So if my GPS device can only claim to be as accurate as what building I'm in, you probably want to go with only maybe 3 decimal places here. Pointing out a specific suburban cul-de-sac. Questions? Cool. So I defined that term, well, I mentioned that term earlier, geocoding. Geocoding is the process of extracting coordinates from addresses, or there's something called reverse geocoding, which is using coordinates to get the address, right? It can go both directions. So let's say we had a list of addresses, like mailing addresses, or even just place names like Lewis Hall or like Romney Gym on MSU campus. There are databases available to us, one of which is maintained by the US Board on Geographic Names. And you can plug in a search to that, something like Lewis Hall, and it will return this information. Latitude is 45.4004 degrees north and negative 111.0303 west. Also has things like our elevation, when that location was updated, etc. So how is this useful? If you want, if you have your device, you can pull up a map, any map in Map Viewer. You don't have to though, you can just follow along. You are probably all pretty accustomed with finding locations on maps. But one of the things we can do on Map Viewer is just click this button down here. And let's say, let's find Romney Hall, Bozeman. What happened there is it took your input as text. It fired up what's called a geocoding database, one of which is hosted on servers provided by Esri. And it found the coordinates of our location in Bozeman. So it ran a geocode, right? It found the coordinates based on a description of the place, a landmark. It actually probably had to use some ranking to say, where do most people think Romney Hall is located? There was probably a few different options returned, but this was the best fit. Note that it actually didn't do a great job at all. It put us in downtown Bozeman. So there are errors associated with this. Let's go to our correct location. And on Map Viewer, what you can do to get your absolute location is click that little wrench map tools down there. And you can hover over a location on the map and it'll tell you the precise coordinates in latitude, longitude with decimal degrees, which is what I'm showing you right now. Base map coordinates. That's kind of interesting. So this is actually pixel values on the base imagery. Degrees and decimal minutes, right? We've got tons of different formats we can report these coordinates in. We can also use different coordinate systems like Universal Transverse Mercator. We're going to learn about what this coordinate system is. Raise your hand if you ever heard of UTMs. One person maybe. Anyone in the military here? Nope. Well, if you were in the military, I'm sure you would have heard of this because this actually was a coordinate system developed for NATO to use a common coordinate system. And the advantage is that the coordinates are in meters. So you can very easily describe distances and locations between locations using this coordinate system. So another thing we can do, right, is we can reverse geocode, which is, hey, let's find our location. Let's use decimal degrees. 45.66, 111.04. And we can just type that into Google, negative 111.04, and see what happens. I typed it wrong, apparently. Negative 111.04. And actually, Google had a search result, right? It already realized from reverse geocoding that we're probably looking for Montana State University places. So it took those coordinates and did the opposite direction of a geocode, which again was referred to as reverse geocoding. We talked a little bit about latitudes and longitudes. I'll go into more detail about what those are, but I want you to experiment with some of these alternative coordinate systems. So if you have your device out, I want you to go to what3words.com and find your location. I'll show you how to do it on desktop up here. I'm on what3words. And this computer is just, well, actually, it does have a little find my location crosshairs. It's going to ask me if it's allowed to actually find my location. And it did a pretty good job. Okay, so once you have found your location, I want you to think about how this coordinate system works. Turn to the person next to you and let's do a minute of conversation about why this coordinate system might be useful, especially compared to something like 45.6603 degrees north, negative 111 point several decimals degrees west. So what might be the advantages of this coordinate system? Ready, go. Okay, so what are some things we came up with? Advantages and disadvantages of this coordinate system. Yeah. You don't have to worry much about the level of detail, the precision, right? That's kind of baked into this coordinate system. So did anyone see that these are actually 3 meter by 3 meter boxes? Anyone have a guess as to why the boxes were chosen to be that size? Kind of like, you know, the distance from me to the front desk here is 3 meters. Any ideas? I'm very comfortable with silence. Yes. Nice. Yeah, that's definitely the goal of this coordinate system, is to make the coordinates a little bit easier to communicate and remember. So that's a great answer. I really like that. So the location that it provided for me was important fiasco rotation. It's always fun to think about whether there's any meaning to these words. Probably not. They're just random. But yeah, so these are actually really easy to remember and communicate. So that's one advantage. But you are limited in your precision, right? So even if you have a GPS device that is capable of getting like 1 to 2 centimeter accuracy, you can't use this coordinate system to be any more accurate than 3 by 3 meters. And to answer my earlier question about why that size was chosen, as we will explore in this course, that's about as good as your phone can do. If your phone is talking to the GPS satellites and you're outside with a clear view of the sky, unobstructed, that is the location precision you can expect to get from a modern smartphone. So this is really geared around people using their phones to find their locations, and the sizes of the cells have been sized accordingly. Any other advantages or disadvantages? So where I first heard of this was that first responders in the UK are actually using this to ask people who call them to provide their location. They say, hey, go to this website, give us the 3 words of where you're at, because they found that people were having trouble with latitude, longitude, right? Communicating a bunch of numbers accurately was difficult for people, much quicker to actually use this coordinate system. And it just provided a more memorable thing. And I think this is a startup company. They're trying to get people to adopt this coordinate system, like, you know, businesses to post the link, etc. We will see if it actually catches on. So takeaways here, there are different ways of expressing your absolute location with different coordinate systems. We're going to learn a lot of them in this course. We will use them in our GIS work to map things, and we also want to understand their limitations as well. The next geographic concept I want to cover is direction. We actually do, you know, this is kind of an intuitive term, but we do have some formalized definitions of direction. This is the position of a feature or phenomenon on the surface of the Earth relative to something else. So commonly in GIS, we use true north, magnetic north, or grid north as our reference point. And these are all different. I have a graphic. Went a little wild with the slide formatting here, but hopefully you can see this. So true north is actually not the same as magnetic north. The magnetic north pole depends on Earth's magnetic field. It does actually move through time. This map over here in the center shows us between 1831 and 2005, the magnetic north pole moved from this location further north towards the geographic north pole, which is the rotation axis of the Earth. And so those two things, they can be the same. right? If we were over in Montana, it might just so happen that if you drew a line, it would go through magnetic north and true north. But in a lot of places, magnetic north is slightly different than true north. And compasses have to actually account for that. Surveyors have to account for that. And then grid north is just where the north-south lines on a map point to. Typically, this is the same as true north, but it can be different depending on what kind of map coordinates you are using. So to describe direction, we can describe it relative to north, but we often also add on to that an egocentric direction. This is relative to our location. So you could say Montana Hall is to the north of me. You could say Reed Hall is to the southwest of Montana Hall. That would be an example of landmark where we're describing a direction relative to a prominent location. Oh yeah, there's Earth's magnetic field. Another view. So we can see all three on this. We have a grid that is pointing to true north. So the grid north following these north-south lines is the same as true north in this case, but magnetic north is different, and it's actually located at the point where this latest star has been mapped. All right, so instead of rushing through distance, I will let you go, and we'll pick up with this on Tuesday. Have a great long weekend. Have fun in lab.